back, Ravens. Get yourselves 3 colored pencils or just a whole group of colored pencils for the rest of these presentations. Pause if you need to. All right, cool. Let's get going. Looking at the major groups on the periodic table. So the first thing we're going to do here is take out that periodic table that's part of your notes. It is the first page of the notes packet, and I want to say that it's page 67 in your binder. Okay. I'll make the caveat that if I use these in future years, that page number may not be true. Anyway, the blank periodic table I gave you. All right, this is the one you're going to color in. I want you to take one of 3 colors and make one color be non-metals. Do not fill it in when you color. Just draw a thick box highlighting all the non-metals because you're going to put a lot of information on this periodic table. Okay, so one color for the nonmetals, one color for the metals, and one color for those metalloids. Okay, pause if you need to. I'm going to move on for the sake of the video. Okay, so the properties of metals, nonmetals, and metalloids. Those are the 3 things we're going to talk about in this part. Let's start with metals. 3/4 of the periodic table are all metals. So metals have physical properties, and remember, physical properties describe those physical characteristics, what it looks like, and that. So all metals have luster. They're shiny. That's the fancy word for shiny. Conduct heat and electricity, some better than others, but they're all able to do it. They have high densities. Remember, density is how close particles are together. So in metals, the particles are very close together. They also have a high melting point. Okay, to break those bonds that hold them being close together takes a lot of energy. Metals, being that they're high density and those atoms like to hold and be close to one another, that makes them be what we call ductile and malleable. Ductile means it can be drawn into a wire. Malleable is pounded flat into sheets. Okay. Chemical properties. Chemical properties describe how elements behave when interacting with other elements. Okay, so when we're looking at chemical properties, we're looking at the characteristics of how well they play with others, or how they go about playing with others, if you want to look at it that way. So metals are always going to give up electrons to form positive ions. I get that you don't know what that means yet, but you will. We have to learn everything in stages. Keep remembering that this is all going to tie in together. Okay, with the next unit and the unit after that, and we all bring it circle round and get it all together. Okay, metals are going to form what we call ionic compounds with non-metal elements. Okay, you don't need to know what an ionic compound is. You just need to know that metals, when they come together with a non-metal and they meet up, they form ionic compounds. Metals also have the ability to corrode and tarnish easily. Corrosion, tarnishing, rusting, when copper gets that green patina to it, that's all chemical reactions with oxygen in the atmosphere. So corrosion, tarnishing, rusting, those are all chemical changes that are occurring due to the chemical properties of metals. Metals like to react with oxygen in the atmosphere. All right, our next group are the nonmetals. Nonmetals are completely on the other opposite end of the periodic table. There are not that many of them. The nonmetals are not shiny. They're the exact opposite of a metal. They're not shiny. They're not able to conduct heat or electricity very well. They're much lower in density, meaning their particles are spaced farther apart from each other. They have lower melting points because those particles are not held tightly together. They can melt and separate and become liquids and move around much easier. They're also what we refer to as brittle. Brittle is the opposite of being malleable or ductile. Brittle are going to break and shatter. If you pound it, it's going to break into pieces. not flatten out. Okay, the chemical properties of the nonmetals, again, still the opposite. This time a nonmetal, pardon me, they're going to take electrons. They add electrons and they form negative ions. Again, this will make much more sense next semester, but we're just introducing all these ideas now. Nonmetals form ionic compounds with metals, same thing, and they also have this special unique ability that metals don't do, is they form what are called covalent compounds with other nonmetals. And we'll get into what it means to be covalent next, a few units from now, actually, before we get to bonding. Okay. Video time. Video time. Play video. No. There we go.
Nonmetals are insulators or semiconductors, and their oxides are acidic. They are highly electronegative, meaning they will gain electrons instead of losing them. Nonmetals form ionic bonds with metals by gaining electrons or covalent bonds with other nonmetals. Hydrogen, a nonmetal, is a colorless, odorless, highly flammable gas. It is the lightest and most abundant element in the universe. Hydrogen is the main energy source for our sun. Two hydrogen atoms are fused together, forming helium and releasing light and heat energy. Carbon is a solid with several different physical forms, called allotropes. It can appear as a dark, brittle material called graphite, or as diamond, the hardest natural substance known. Nitrogen, as a gas, is colorless, odorless, tasteless, and inert. Nitrogen makes up 78% of Earth's atmosphere and is an important component of many proteins and fertilizers. Oxygen is a colorless, odorless gas, abundant on Earth, and necessary for the support of many forms of life. Oxygen is formed primarily as a result of plant photosynthesis. Phosphorus has three main solid allotropes: white, red, and black. Because it is highly reactive, it is never found as a free element in nature. Pure white phosphorus ignites spontaneously in air. The red allotrope is used in matches. Sulfur, once known as brimstone, is a yellow crystalline solid. It was a main ingredient for medieval alchemists. Selenium is a gray nonmetal that conducts electricity better when exposed to light. It is also a trace element that helps the thyroid gland function, but many of its compounds are extremely toxic. There are far fewer nonmetals than metals on the periodic table, but nonmetals make up most of the Earth and its organisms. Because of their high electronegativity, the gaseous nonmetals exist naturally in a diatomic state. Hydrogen, nitrogen, and oxygen form molecules made up of two atoms bonded together. This molecule is much more stable than a single atom. Phosphorus, sulfur, and other nonmetals also form polyatomic molecules. Phosphorus makes pyramids of 4 atoms each, and sulfur exists naturally as a ring of 8 atoms. This tendency to form polyatomic molecules can be explained by taking a closer look at the periodic table. The elements are listed in order of their atomic number, which represents the number of protons in an element's nucleus. In its normal or ground state, this nucleus is surrounded by an equal number of electrons. As the atomic number increases, generally so do the size and mass of the atom. As you read the periodic table from top to bottom, each horizontal line is called a period. This represents the number of electron shells the element's atoms normally have. For example, an atom of nitrogen has 2 electron shells, so it lies in period 2. And an atom of selenium in period 4 has 4 electron shells. Each of these shells can contain up to 8 valence electrons. As you read the table from left to right, the vertical lines of elements are called groups. Elements in one group have the same number of valence electrons in their outermost electron shells. These are called valence electrons, and they usually dictate how elements interact. The nonmetals are to the far right of the periodic table. Not including hydrogen, they span groups 14 through 16 and have anywhere between 4 and 6 valence electrons. Hydrogen is in group 1 above the alkali metals, but it behaves as a nonmetal in most circumstances. It has 1 valence electron, but its valence shell is complete with 2. The type of bond a nonmetal forms depends on its own valence electrons and on the type of element with which it is bonding. Generally, nonmetals will share electrons with other nonmetals in a covalent bond and take electrons from more electropositive metals in an ionic bond. Carbon, with 4 valence electrons, has the most flexible bonding properties. It usually does not form ionic bonds, but it is able to form rings or long chains by bonding with itself. This versatility accounts for the wide-ranging appearance of carbon's allotropes. Oxygen, with 6 valence electrons, will take electrons from metals to bond ionically. In fact, when any element is oxidized, it gives up electrons. Nonmetals may be a minority on the periodic table, but they make up the majority of the world around us.
Okay. All right, so let's move on. Oh, going back to the video, 2 terms you want to be familiar with. They're in your textbook in Chapter 3, Section 4. Allotrope is an important word to understand, as well as diatomic. Those are words that'll come back in the future. All right, let's move on to the third of our 3 major groups on the periodic table, and that is the metalloids. Metalloids exist in this fuzzy place in between metals and nonmetals. They have properties that are a little bit of both. Some may be more like metal, some may be more like a nonmetal, but either way, they're in the middle here, and they're a little bit of both. So they can be shiny or they can be dull. They can be ductile or malleable or brittle. Okay. Some conduct heat and electricity better than nonmetals, but not as well as the metals do. Okay. And then, what happened to our physical properties? Oh, just physical properties. Chemical properties, they have a mix. Sorry about that. Confusion going back and forth. The chemical properties of metalloids is that they can give electrons or they can accept electrons. Okay? They will do what the situation best allows for them to do. So there's a variety of things. Anyway, let's watch a movie on metalloids. Can explain things better.
The metalloids reside between the metals and nonmetals on the periodic table. They exhibit some qualities of metals and nonmetals. Many metalloids act as semiconductors by behaving as electrical insulators at room temperature, but electrical conductors when heated. This property is vital to the computer industry. Boron is a yellow-brown crystal. This non-metallic element is used to make high-strength and lightweight aerospace equipment. When it burns, boron gives off a distinctive green glow, so it is a main element in green fireworks and flares. Silicon is a hard, dark non-metal. It is the second most abundant element and makes up 25% of the Earth's crust. A large part of sand, clay, granite, and quartz is silicon. This useful element goes into solar cells, tools, cement, grease, and perhaps most importantly, semiconductors and computer microchips. Germanium also goes into computers and electronics. This hard, brittle, gray-white metal is used to make transistors, semiconductors, infrared optical instruments, and wide-angle camera lenses. Arsenic is a gray, brittle non-metal. It is is a deadly substance that has been used to make rat poisons and insecticides. It is also used in the manufacture of metal alloys, mirrors, glass, lasers, and semiconductors. Arsenic is a byproduct of copper forging, and it could provide evidence about when our ancestors began to make copper tools. Antimony is a hard and brittle blue-white metal that is a poor conductor of heat and electricity. It helps make lead alloys more durable, and it goes into flame-proofing materials, lead batteries, mascara, paints, glass, pottery, and plastics. Tellurium is a silver-white metal-like non-metal. Small amounts of this element are added to copper and stainless steel alloys to make them easier to work with. It also colors glass and ceramics. The rare radioactive metal polonium is used to make nuclear batteries. It is currently under consideration as a possible heat source on spacecraft. Small amounts of polonium are used in shielded brushes that remove dust from photographic film. The metalloids are a diverse collection of elements. Most are brittle, somewhat shiny solids that exhibit properties of metals and nonmetals. Some of them, such as antimony, have the appearance and luster of metals. But others, such as arsenic, clearly appear to be nonmetals. Their chemical properties range between those of metals and nonmetals. One of the most unique properties is semiconductivity. Acting like nonmetals, semiconductors block electric currents at room temperature. But when they are heated, they act like metals, allowing electricity to flow through them. This unique property makes the metalloids, particularly silicon and germanium, valuable to the computer and electronics industries, where semiconductors are used in everything from calculators to computer chips. The unusual appearance and behavior of the metalloids can be explained by taking a closer look at the periodic table. On the periodic table, the elements are listed in order of their atomic number. The atomic number represents the number of protons in an element's nucleus. In its normal ground state, this nucleus is also surrounded by an equal number of electrons. As you read the periodic table from top to bottom, each horizontal line is called a period. Each period represents the number of electron shells the element's atoms normally have. For example, there are 4 electron shells in an atom of germanium, so it lies in period 4. Meanwhile, an atom of polonium, in period 6, has 6 electron shells. Each of these shells can contain up to 8 valence electrons. As you read the table from left to right, the vertical lines of elements are called groups. Elements in one group have the same number of valence electrons in their outermost electron shells. If an element has 8 valence electrons, as the noble gases do, its outermost shell is completely filled, and the element generally does not react chemically with other elements. If an element has less than 4 valence electrons in its outermost shell, as most metals do, it is electropositive, which means it tends to give up its valence electrons to other elements during chemical reactions. If an element has more than 4 valence electrons, as nonmetals do, it is electronegative, which means it grabs electrons from other elements during reactions to fill its outermost shell. The metalloids form the line that runs between the metals and nonmetals on the periodic table. They span groups 13 through 16 and have anywhere between 3 and 6 valence electrons. The atomic structures of the metalloids lie squarely between those of the metals and nonmetals. For example, boron has 3 valence electrons and usually acts as a metal by shedding its valence electrons during chemical reactions. Arsenic, antimony, tellurium, and polonium have more than 4 valence electrons, and they typically act as nonmetals by gaining electrons from other elements. Meanwhile, silicon and germanium, with exactly 4 valence electrons each, sometimes act as metals and other times as nonmetals. The metalloids and their great variety of properties are valuable for many industrial materials, from transistors and semiconductors to ceramics, solar batteries, and certain polymers. The metalloids may be the strangest and most useful of all the element groups on the periodic table.
All right, good job. Let's see what's next. Part 3. Okay, see you next time. Part 3.